Good afternoon and welcome to our presentation, Don't Give Me Any Friction, the Magic of Sintered Bearings. My name is Brian Sexton and I'm an automotive technical writer for Babcock's Media's Shop Owner publication and the moderator for this event. Today's webinar is sponsored by Mevotech. When it comes to friction surfaces on any suspension joint, sintered bearings are the optimal choice. Lifecycle testing has shown sintered bearings to be better performing and much more durable than the other materials. In this webinar, you'll get an inside look into each ball joint technology, which will help you determine which bearings are right for your customers. First, I'd like to address some housekeeping items. As part of this webinar, we will have a live Q&A session. Our speaker today will address as many questions as they can during the last portion of the event. Please submit your questions throughout the webinar. To improve the chances of your question being addressed, don't wait until the end of the event to submit it. Ask it as it occurs to you. To send in your question, type it into the Ask a Question box, then click the Submit button. This webinar is being recorded and it will be available on demand for you to view at a later time. We encourage you to direct coworkers to the recorded presentation. You'll receive an email with a link to the on-demand version in a few days, and it will be posted on the Shop Owner brand websites. Looking at the widget bar at the bottom of your console, you'll see icons which allow you to open and close windows on your screen. When you place your cursor over any of the icons, you'll see the name of the widget. You'll notice there's an icon for Facebook, as well as an icon that lets you send an email to a friend about the webinar. There's also an option to print a certificate for attending today's webinar. You can access this by clicking on the yellow certificate icon. If you need help at any time during the webinar, click the question mark icon for a few troubleshooting tips. And finally, if the slides stop advancing, or if you're having problems with audio, try pressing the F5 key at the top of your keyboard. It will refresh the webinar console on your screen. Now I'd like to introduce our presenters. We're happy to have Victor Moreira joining us today. Victor is the Technical Services Manager at Mevotech and has been on the team for over 5 years. He spent over 20 years in the industry working on all types of vehicles, from heavy-duty trucks to exotics. A Canadian Red Seal 310S certified automotive technician, he spent a good part of his career in independent specialty shops. And we also have Mac Chastain joining us today. Mac is a product specialist at Mevotech. He was a shop owner for over a dozen years before joining Mevotech 5 years ago. As a product specialist, he brings his 17 years of industry experience to ensure that Mevotech stays ahead of the competition in aftermarket quality and coverage. Mac believes the best products are the ones that make a technician's job easier and work harder for the end customer. Now let's get started with today's presentation. Mac, the floor is yours.
All right, well, welcome everybody. Appreciate everybody tuning in here. Let me just advance that soon. All right. Victor, you gonna grab this slide or I'm gonna?
Sure, Mac. So,
okay.
Thanks again to everyone for having us. Thanks, Brian, for that awesome introduction as well.
Yeah.
Today we're going to be talking about bearings, and specific sintered bearings. We're going to put a lot of focus on that. But first, we're going to get into a little bit of an agenda to find out what exactly ball joint bearings are, the different technologies that have been used to accomplish what a bearing does throughout the years. We're going to look in specific on the three main technologies used nowadays, which is true metal on metal, sintered metal, and polymer. And then we're going to actually look into some data that kind of puts out forward why sintered bearings are the superior choice when it comes to these types of technologies. So to start off, Mac, what are ball joint bearings, right? And I'm not sure. I know, Brian, you've held a significant amount of time in the Bay as well. Was this something that you were kind of familiar with? Like, I know when I was working on cars, I didn't really have time to break open ball joints to find out how they worked, right? It was just kind of replace the bad one with the good one.
Yep. Most of the time, the extent of it was, does it have a Zerk fitting or does it not? Is it serviceable, greasable?
That's exactly it, right? Well, Mac, I know you travel a ton, and you're kind of always talking about bearings in the shops and whatnot. But it's pretty simple, right? It's just the material that kind of gets used as a buffer material. You know, the ball joint, we find it all throughout nature in different anatomy, even in our own, our elbows, our ball joints. They're very simple.
Whether it be our hip joint or our shoulder, it's just that material in between that ball spear socket and then our bones. Same thing in the ball joint, and they can be of a couple of different materials, but it's that buffer zone, it's that wear zone. It's actually what determines the wear life, or what we would call the life cycle of that joint, whether it's a tie rod end, whether it's a ball joint, or in a control arm. So. Now, and to Brian's point, whether it had a grease fitting or not, I know for all the years that I worked in the industry, most of the time I wasn't cutting stuff open and looking inside, but it's a real plus to be able to see inside of it, because a lot of times when you see how things are designed or made, sometimes that changes what you purchase, what you put in, and sometimes even how you install it. If you know how it's manufactured and built. So
exactly, that's exactly what kind of we wanted to kind of present this for too, is to kind of bring people into the inner workings of it, have a good understanding of the component, and again, like any specific item on the vehicle, just going to advance. It does come with a certain really important criterias, right? It's got to accommodate and meet a lot of different characteristics so that it can perform and do the job that it needs to do, right? So one of the more important things I find is it's low deformation under stress and high stability throughout its lifetime. These bearings have to suffer quite a bit of impact, and they can't be deforming under that impact. They have to provide a service life, but we can't make them extremely hard either, because it's a wear surface, it's a friction surface. And so then it becomes the battle of the two materials, and whichever is the weakest is going to lose. And if it gets accelerated if we make it too hard, right?
Yeah, and again, that's one of the reasons why it has to be the flexible design options. And as you alluded to, it can't be too hard, or it's going to be brittle. It can't be too soft, or it's going to wear fairly quick and not have the life cycle or the life expectancy.
Yeah, and they have to accommodate, like we're speaking ball joints, but in reality, we're talking ball and socket joint. So we're talking tie rod end, we're talking stabilizer links, anything that has that ball and socket joint is what we're kind of speaking about today. It all uses the same technology. So, the bearing in a stabilizer bar end link is going to be much, much smaller than a ball joint that you're outfitting on an F450, for example. Right, so you do have to have that flexibility in terms of making it much smaller or much bigger, right? The next item would be heat resistance. This is becoming more and more important as kind of the years go by. Automotive manufacturers are really pushing these ball joints out and these joints, cramming them into tight areas, putting them really close to high heat objects like brake rotors and even electric motors nowadays and whatnot. So heat resistance is huge because they are fairly close to a lot of other components that generate a tremendous amount of heat.
Yeah. And in your exotic and high performance applications that are starting to get carbon ceramic brakes, you've got an even hotter brake heat source right nearby.
Oh, definitely. And they really try and push the pivot points out for the sake of steering axis inclination. They really try and push them out as far as possible, to the point where we've actually done some case studies on a lot of vehicles where they're cutting out the brake shield, the heat shield and dust shield of the brake. Yeah, so that they can have space to push the ball joint out as far as possible. And it definitely soaks up a lot of heat.
Yep.
Chemical resistance or the grease used in lubrication and other environment factors are an issue also. Depending on what kind of a bearing that you have in your ball joint, whether it be your control arm or your tie rod end or that ball and socket setup, they really have to hold up to the chemicals, whether or not the lubrication that you use, you don't want that to attack it or to be detrimental. And then, of course, just the environment, dirt, debris, a little bit of salt, a little bit of sand gets past the boot and it gets inside of it. So that material has to be able to withstand that, the greases that you put in it, and of course the contaminants could get inside.
Yeah. A low coefficient of friction is always really important too, because again, depending on the vehicle, we really can't have a joint that is so high in friction that you actually start building a material trade-off. Like the actual term is called fretting corrosion. It's just so much friction that it actually tears material away from the bearing surface or the ball sphere, and then that just becomes its own contaminant. And also, again, as vehicles get smaller and lighter, there's a certain smoothness that needs to kind of relate to it. It's really tough to have a ball joint, but I guess being technicians, all of us, we've all had that creak snapping ball joint that comes in. That's so dry that as you turn the wheel side to side, you literally hear it snap, pop, and let go as it's kind of rotating in the socket. So there has to be a considerable amount of effort put into the amount of friction that's going to exist inside this joint right off the bat.
We'd call that the arthritic joint in our shops.
Yes. The problem is when that snap popping sound goes away, right?
They think it healed itself.
Yeah, it doesn't.
Yeah,
it just
after
made
that
a lot more
snap popping goes away, then something more catastrophic usually happens when you hear it, and for a little while, and then all of a sudden you don't hear it anymore, and you think, oh, it's okay, it went away. Well, it's on its way out in a big way most of the time. Low wear factor is another thing to consider. You know, the bearing materials that we use, they're just going to have to be able to stand up. You know, and there are some designs out there that are a little more cost effective to manufacture and to produce, but the wear factor is just not there on some of those. And they do a pretty good job of making it last what I would call the period that the vehicle's under warranty, or that wear life. But yeah, it needs to have a low wear factor. It needs to be able to withstand some higher loads and some tough driving conditions.
Yeah. The next item is high endurance and strength. Now, this is extremely important, particularly in the aftermarket. Again, we've spoke about it a number of times. As a vehicle ages, it is definitely not the same as it once was when it came off the assembly line. Everything starts to get a little looser. The various components that are wearing start to affect other components, and they kind of play off of each other. So designing a ball joint as a replacement ball joint for the aftermarket, you really have to take this to the next level to make sure that you're building a component and using the right materials to get the service life that you're expecting out of this component, right? And it becomes more and more challenging, especially as the vehicles start running into an older age bracket.
Good durability, reserves, of course, you know, to address the extreme situations, you got heavier loads that you're going to carry. Maybe the vehicle's driven off road, you're up and over curbs. So the durability has to be there. So the material, again, is going to have to really perform under those conditions and have a decent wear life in those harsh conditions.
Yeah, unfortunately, in a perfect world, we'd all be driving over freshly packed asphalt, but that is not the case. And so, yeah, you have to have these reserves inside. It's got to be prepared to take these impacts and these high load, abrupt situations so that every little nuance isn't a catastrophic one. Let's put it that way, right?
Yeah, and of course, to add to that, the roads aren't getting any better, that's for sure, as they degrade and erode away. I just don't know that we can keep up quick enough with maintaining or repairing that. That's the roads that we travel on that are out there. Just the further north you go, the environment just wreaks havoc, so some real challenges for the pothole and the roughness of the road, which doesn't lend itself to a long life to some of the designs that are out there that are cost effective to manufacture. Yeah,
exactly. So in speaking about that, now we'll actually kind of have a look at the different bearing technologies that have kind of been used throughout the years. Some of them are pretty much obsolete. They just don't exist anymore. They may be still a couple floating around, but it's definitely not anything that any late model vehicles will be implementing. The first being the old spring design, and it pretty much just literally a steel plate as a backing plate. That was your wear surface. That was your bearing surface, was a little piece of dented sheet metal, and it was kind of spring force loaded from the back. I think, Mac, actually you have one there, right?
Yeah, I don't know how well you can see that, but I actually had something that was cut open. It's an earlier one. And unfortunately, I don't have the little spring that was in there, but that actually is what made it up against the ball spear. And then, of course, you had you had what looked like a little valve spring that seated in the bottom of it that kept tension or pressure on that unit. So interesting, but been a while since
what they had at the time, right? It was the way to engineer your way out of a problem at the time with the technologies and materials. And you know, I think up until some 90s, I believe Toyota pickups actually still had these as their upper ball joint. So it's not really that long. Well, again, I'm showing my age. It's not. The 90s was quite a while ago, but it's not something that would be used anymore. It's pretty much been obsoleted. The next one we have is the wear indicator type, very similar to the spring-loaded one, except it would use a type of malleable material that would wear. And as it would wear, the grease fitting would actually kind of get pushed further up into the actual housing through the backing plate. And I know some GM vans from again, the late 90s still had these. And pretty much you knew the ball joint was done when you couldn't connect the grease coupler to it anymore. It had receded so far up into the housing. But again, very similar to the first spring-loaded system, obsolete. Now, again, these are still, you know, you might get caught off guard every now and then. These are still kind of around. It's not the best bearing technology, but I guess for the time, again, it worked, and it's what they had to work with. I don't believe any new model vehicles are being built with any of these receding grease fitting types. The next one is what we call actual metal on metal. Now, this is a term whenever you hear it's a metal on metal ball joint. This is kind of where your head should kind of go to. And it's pretty much everything gets milled out of a housing. And there really is no bearing surface. It requires constant lubrication to have any type of friction prevention against it, or to kind of fight off the friction. And once it goes dry, it's pretty much downhill after that. These are actually very susceptible to that fretting corrosion. Once it goes dry, it starts to kind of chip away at itself, creates its own debris, and then just wears itself really quickly. Very.
You're right, Victor. That metal on metal design, once it dries up, it goes away fairly quick. As you mentioned, as the metals, they work against one another. Even though initially I'm sure that the bearing area or the lower housing is a tad bit softer than the ball stud. That's usually what happens when you have two pieces of metal that work together. One of them has to be the sacrificial or wear point. But in this design, when the grease goes away, you're exactly right. That fretting or galling happens really quick, and it just destroys that surface or the two mating surfaces super quick.
Yeah. This design also needs to be spring-loaded to some degree, because you can't really pack all this stuff in and then just roll form it shut. It'll either be too tight or it'll be too loose. So you need to have some sort of a spring method in there. And usually it's done with either a wave spring or a Belleville washer. But it does require a little bit of spring force as well to kind of help maintain that sweet spot of tension. And again, what would be the perfect world with, properly lubricated and doesn't have any of these other elements being affecting it. The next technology is pretty much the more common play nowadays, what you're going to see in majority of the OEM vehicles out there. And it's your polymer bearing. It's quite literally a plastic cup.
Yep, about 99% of time, everything that rolls off of the assembly line, this is what's going to be in there. And there's variations of it. I think, Victor, you have some examples of it there. And then here's one that's really a small bearing or a small mating surface there. It's got something here that's a little bigger. But again, probably a little different mixture of polymers in there along with the plastic. But you know, we wonder why this type of manufacturing is happening, but part of that reason is it is so much cheaper to manufacture this plastic. I'd say you could probably knock 10, 15, 20 of these out of an injection mold, or a mold that probably holds 10 or 15 of them, quicker and more cost effective than you could machine or manufacture a bearing. So that cost is really driving it. And, you know, I will say one thing for the OEs in this setup, Victor, and you can probably speak to it also. They've done a pretty good job of making it last what I would call at least the warranty period, 336, you know, 550, you know, maybe in some cases a little bit longer than that. But for the most part, the math is what's driving this design. It's super cost effective to manufacture it in this way, but it does have a few challenges.
Yeah, I do have a couple of examples here. You can see very easy to manufacture. You can make it in any shape or size, and even down to the assembly of it. You know, it's quite as simple as just snapping it onto the ball stud, and then it gets inserted into the socket of the ball joint, and it gets roll formed over top, and you have your ball joint there. You know, so in terms of ease of manufacturing, cost effectiveness, from the manufacturer's standpoint, you know, it does the job great while the vehicle's brand new. You know, everything's nice and tight. It operates the way it needs to be, and they certainly get the life that they need out of them. So as a vehicle manufacturer, yeah, this will definitely be the next step up from your older traditional steel plate and spring style, let's just say, right? Yeah. And again, though, just to show that some of them are a little more robust and strong, but then you do get the flip side of the coin where some of them, you know, don't even look like they should be used as a bottle cap. They're very thin and you wouldn't get much wear life out of something like that.
Yeah, definitely.
All right, so how are they made, or what are these plastic bearings made out of? And so we're going to try a little enunciation game here. So there's usually two different types of mixtures, or you have a polyoxymethylene and then a polyformaldehyde. But again, it's a material, it's a mixture, it's heated up, it's almost acts like an extrusion, it's pressed into your injection mold, of course, and then it cools and then you separate it out. But very cost effective to do this. So that's kind of what you're looking at roughly. And depending on, you know, one manufacturer may use a little different mixture of plastics and polymers together than another one does to try to help the wear life and the impact resistance of the product. But that's the majority right there. It's actually a really good picture of how it's manufactured.
Yeah, it's simple plastic extrusion. And like you mentioned, it depends on your die setup. You can pump out 1, 2, 10, 100 at a time and quite literally just have them made out like that. Very cost effective to manufacture. But again, they do have their list of pros and their cons. It's not the greatest thing since sliced bread, unfortunately. I think the biggest pro is definitely its low cost. That's why it's been driven to the point of being used pretty much across every automobile that's being pushed off the assembly line today. That's a huge driver, of course, for any automobile manufacturer as well. So you can see why that one would make the top of the list as the biggest pro, right?
Yeah, agreed.
Ease of manufacturing, we spoke to that. It's just really simple, and I think Victor did a great job of just kind of snapping it together and putting it in the housing there, and you could just see how quickly something like that could be put together. No hands needed, of course, probably robotic, and then a piece of equipment comes up and rolls the top of the flange down and locks it in there. So just a real simple, easy way to manufacture it, and again, it's really gets married together with the low cost. It's part of that also because it's so easy to get the job done or to get the process done.
It's lightweight. That's also a big factor in today's world is the definite attention that the vehicle manufacturers put out to the fuel consumption of their fleet. And they, we've said it once, we said it a million times, Mac. They're cramming so much more weight in terms of infotainment and accessories, cameras and sensors and all this other stuff that they're kind of sabotaging what they're trying to do by lightweighting. So they're really, really going for as much weight savings as possible. And yeah, when you measure up a plastic bearing up to a big spring and a steel plate or a sintered bearing or a full metal housing, it definitely does come up in terms of being much lighter in weight, right?
Yeah. Yep. And the weight is really the one thing that makes the huge or the biggest impact on fuel mileage. If you can get that vehicle down in weight, and it's going to come from a handful of different places. Anywhere a plastic part can be put in place of something that was metal, whether it be a larger or a smaller part, you're certainly going to see that. I know that we have the active fuel management, variable valve timing, all of those things play into that fuel mileage, but weight is really still the number one factor. If you can get that down, it contributes to helping the fuel mileage increase.
Yeah, it's unfortunate, though, that most people will buy their car and then load it up with a bunch of unnecessary stuff and drive around with it. I know I'm like that. I have my baby stroller in the trunk all the damn time, and, it gets used once or twice. Yeah. So it's unfortunate. It's really, again, coming off the assembly line, getting it tested, that's the standard that it met. And that's where the lightweighting really, that's where they're trying to achieve those numbers. It's unfortunately, once the vehicle gets into the marketplace, that lightweighting really doesn't help your fuel economy, unfortunately.
Yeah. I remember the first time I saw that there were manufacturers out there switching to aluminum fasteners, bolts and nuts on certain systems. And my thought was, why could they possibly think that this is the way we need to go? BMW with their water pumps and thermostats, those are aluminum bolts to hold them in. And then I disassembled and parted out a car, and I had a 5-gallon bucket full of bolts and nuts. And then I understood, if every single one of them was aluminum, it would have made a difference of 80 or 100 pounds of curb weight on that car I took apart.
Oh yeah, so it all adds up. It all adds up.
Every ounce matters.
And a lot of it, Brian, as you mentioned, some of that stuff is not reusable. A lot of things that are designed like that are torque to yield. You get a one-time shot. You get a one-time stretch, because we all know that steel doesn't respond and react the same way that aluminum does, especially if it's a fastener.
But you can see different to that point, Brian. If anybody's ever had a set of BMW AC compressor bolts in their hand that are about at least 5 to 6 inches long, and they weigh absolutely nothing. I think a sheet of paper weighs more than those bolts. You really see to the extent that they go. But again, we just had actually a question come through that I think it's better answered now than later, is the weight difference in reality between a sintered bearing and a plastic bearing, and depending on size, but equal vehicle, you're looking at maybe double the weight. But at the same time, we're talking maybe about 2-3 grams, maybe at the most. Yeah. So, in terms of the large scale of the vehicle, there's not much of a weight difference between the two. However, like you so eloquently put it, 30 or 40 bolts, a little bit here, a little bit there, it all really adds up.
Yeah, it's that combination of plastic parts that are being replaced, or, it's not just the one pointing out and say, hey, this helps.
It's everything now. You know, it's radiators, it's intakes. Somebody actually just chimed in and said that's why some intakes are. There are a ton of intake plenums now that are all just, you know, that plastic composite. And
if you would have told me 20 years ago that there would be some motor parts, an intake manifold would be plastic, I would have laughed you.
Yeah.
It's commonplace now.
The oil pan on my Volkswagen is plastic.
Yeah. See, so again, easier to manufacture. Materials might be less expensive. So it does. Unfortunately, you know, if you had a steel oil pan and you ran over a rock, it might get a little bit of a bend and a crush, and then things might carry on their merry way. With a plastic composite one, that's probably not going to be the case. So we do make sacrifices, right? Moving along to our list here, you got a very good friction coefficient with these plastics, right? Plastic already it can be molded to be very, very smooth inside. It also has good lubricity to it. So there are some benefits. It does make a good friction material right off the get-go when the car's brand new. Now to the con side. These things are extremely reactive to contamination. You get a little bit of water, wash out the grease that's in here, a little bit of dirt. The ball sphere and the bearing surface are very smooth. And they need to be very, very smooth, because any type of aggregate or anything that would get in here and start to mar up the surface, you would lose all the benefits very quickly. And unfortunately, that's usually the side effect. A little piece of dirt or water will get in, start to scratch up the ball sphere, rust will build up, and then it's all pretty much downhill from there in a few weeks, right? So they're not very good for that, unfortunately.
Deforms easily. That's another unfortunate downside. It just doesn't have the impact resistance that your sintered metal bearing or even a metal on metal design is going to have. And we can't rule out the heat either. I know that we spoke about that a few slides earlier about the heat and how it's creating some challenges. And it centers around the OEs using aluminum, again, to save weight. And inside the aluminum control arm is a polymer or plastic bearing that's very close to a brake rotor. Stop and go traffic, we all know a brake rotor gets warm. That's normal. But unfortunately, in some applications, that arm is so close to the brake rotor, it pulls in some of the heat. And once it starts to warm up, it starts to distort or deform the polymer or the plastic inside of there. And I'm not saying it happens overnight, but the heat is always there, and it shortens the wear life of it quite a bit. So it deforms fairly easy, especially in that environment.
Yeah, definitely. The high heat situations, they don't fare very well. They just, like you mentioned, they get soft, they start to deform, and then they don't spring back. Another thing, and this depends on what side of the fence you're on. A lot of guys think serviceable components are the way to go. Others will argue that, you know, they prefer something that's sealed and that they don't have to mess with. But I have really never met any machinist who has made the argument against, if you can relubricate any moving joint, you are going to get much more service life out of that joint. And again, having the ability to be serviceable is a huge advantage. But unfortunately, most plastic bearings are non-serviceable, and for very good reason. A lot of the actual greases that would be used to service them are actually corrosive against the plastic, and over time would make them brittle. So it's kind of counterproductive introducing your regular type of axle grease or any other grease that would be available to most technicians in the shop, because it would be corrosive against the plastic and can actually compromise the life rather than introducing and rejuvenating it.
You know, that's an excellent point, Victor, because there are some manufacturers that have a plastic or a polymer bearing with a grease fitting combined with it. And I'm not saying that that's all bad, but the petroleum-based products or petroleum-based grease products, like you mentioned, are going to soften and be corrosive to that plastic or polymer mixture over time. So if you shoot it in there and it's a petroleum-based product grease and you think you're doing yourself a favor, you're really working against yourself. It just would require a synthetic or a lithium-based grease will not attack most of those polymers or plastics. It really
depends on what type of plastic that is being used.
Yeah, right.
And it's more often than not, that's an unknown. So unfortunately, it usually goes the wrong way, right? So again, we covered why it can't be covered lubricated with your typical grease. And again, once that little bit of lubrication that it gets sealed with is gone, it wears itself down pretty quickly. You know, it is just plastic. It'll start to wear away. Once it starts to make a little more space, you get into that deformation, you get into that wear, and it's really rapid, the amount of wear that you can introduce once it begins. And there's an example actually of one that's actually worn through due to heat cycling. And you can see it's just a matter that was the side that was closest to the brake rotor. As it warmed up and the person turned the wheel side to side, it just kind of would press against it and bore its way through. And eventually that just showed itself as play in a ball joint that would just be knocking around a little bit when it went in for service. So now, Mac, we'll get into the actual sintered bearings. They usually work as a pair. You have an upper bearing and a lower bearing. And it does work with a spring washer or a Belleville disc to kind of adjust the tension and keep that tension as you may get through a little bit of wear on the bearings. They wear very little, however. You know, when we talk about the wear cycle in a sintered bearing, we're talking, you know, 1/10 of a thousand. Like, it's very, very small bracket that we're talking about. They don't usually wear out very much, but we do have a spring washer in there to compensate.
So the sintered metal bearing process, or as we use that term, sintered metal, you know, what are we saying, or what are we talking about? What type of metal is that? And so it's actually not new technology. It's been around for quite a while, but it's a mixture of different metals in a powder form, and of course, depending on the application and what you're trying to accomplish with that bearing is going to determine kind of the mixture of metals that you put in there to get the right outcome or the longevity or the life cycle of whatever you're trying to create in the bearing. So simply put, it's just a mixture of different metals in powder form. Of course, it gets mixed up and then it gets pressed or compressed into the form or the design of a bearing, and then it goes through the sintering process or a sintering oven. And as it heats up and then as it cools down, it goes through the heat treating process. And then when we're done, we have a metal bearing really that is porous. And not to say that we could do it here on live, but if we were to cut one of these bearings in half, and if we had a strong enough magnifier or cheater and we could look at it from the side view, it would almost look granular or porous.
Actually, fun fact that you said that, Mac, is I do have a cutaway here, and you can kind of see the graining in the end of the bearing here. You can see how it's not a nice piece of shiny metal the way you kind of get with the milled metal over here. It's actually got the grain structure. And again, it's a huge benefit of it not ever getting to that molten point where all the powders just kind of get pressed together. And I have a bunch of different examples here of all the different sizes and shapes that you can make these. And if you actually rub them, you can feel the oil surface that is kind of constantly being exposed through it because it has been permeated with the grease, and it's kind of just like a sponge. It's soaked in that grease, and now it doesn't matter how much you'd wipe this or try and clean it off, it'll always have a nice kind of oily surface to it. But again, another huge benefit of it, similar to the plastic bearings, it's not injection molded, but they are pressed, and you can press them into any shape that you would like. And again, it really helps in our situation because we're trying to accommodate different ball joint types, different sphere types, different loading angles and whatnot. So again, I just wanted to make sure we can actually see what a sintered bearing looks like outside of its housing, and see that, you know, again, there are a lot of different types and shapes available to accommodate the different ball joint sizes and different type of duty cycles that they need to kind of go through.
Yeah, and the important thing here to take away is that when you say metal on metal, that is a different world from sintered metal.
Exactly.
It makes all the difference in the world when it comes to the life cycle of the wear and what happens as it's greased and how it kind of further permeates into the porous portion of the metal. So huge difference in metal on metal and sintered metal, especially when it comes to the life cycle testing.
Exactly, yeah. So now let's get into the pros and the cons of sintered metal. Because again, like everything, actually, this is actually a great little clip of how it kind of works when you grease it, and just a representation. So when the part gets greased, you already have grease existing, and again, the bearing never actually gets molten where everything kind of liquefies. It just gets heated and fuses together, but it remains, all these little spaces remain. It kind of makes it like a little mini metal sponge. And again, it's just a great friction surface for a lot of good benefits that you don't get with other technologies that come in using a sintered bearing opposed to any other technology. Now we have our list of pros and cons. So the first definite benefit of this is high impact and load handling, right? Unlike plastic, you can definitely throw a lot more weight, a lot more impact at a sintered bearing. It is a lot harder. It's a lot stronger. As Max said, this is not a new technology. You will find sintered bearings being used from, I think they go way so far back, I don't even want to actually say a number because I'm going to be wrong. But this is definitely the material of choice. Again, the only reason it was kind of moved away from is that it kind of lasted a little too long. It's unfortunate, like a lot of things on vehicles, you know, you never used to have to change a water pump as often as you did in the cars that came from the mid-90s, like the ones that were far back in the 70s. And you know, there weren't so many electrical issues with corroding connections and corroding cables. And I think this is just unfortunately a technology that was too good for its own sake. And the OEMs moved again to something much more economical and easy to manufacture, because or else they would be still using these. And a lot of OEMs still use, where it matters, you're still going to find sintered bearings in some of the heavier duty applications.
Excellent wear resistance. Victor pointed to that in previous to high heat. So a handful of applications are going to have what we spoke about earlier, a control arm that's really close to a brake rotor. And that's just one example of heat being a problem. And we actually have come up with a patented design in a control arm that, of course, we use this sintered metal bearing, and the heat's not an issue there. So it holds up to the heat extremely well and has a tremendous wear life.
Yeah. It's, again, a definite competitor in low friction. The difference in friction between your plastic bearing and your sintered bearing is a few foot-pounds in rotational torque, 2 or 3 foot-pounds of rotational torque. In reality, even though there is that difference, we're talking a difference at 2 to 3 foot-pounds at 2 or 3 foot-pounds. So, you know, if a plastic bearing ball joint puts out 2 foot-pound of rotational torque, same ball joint in sintered may put out 4 foot-pound of rotational torque. The steering effort of your average vehicle is 300 foot-pounds. So it's really not even an issue. The difference in friction between the two is fairly negligible. There is no real difference.
I'm glad you busted that myth, because I in the field I get asked that often, and the easiest way I can explain it is, grab your torque wrench and torque something to 15 foot-pounds, and then torque it to 18 foot-pounds, and tell me if you can feel the difference. It's just such a small amount that's not noticeable, or that would be hard to duplicate if you had to replicate the same torque, unless you dialed your wrench in. But it's such a small difference, and the power steering overcomes it by a ridiculous amount. So it's not even an issue.
It's an unfortunate thing, but as technicians, a lot of times what we'll do is we'll grab a joint by hand and go, oh, wow, that's a stiff joint. You're not as strong as a car, unfortunately. When you put that attached to a steering rack or a steering system, a conventional steering system, items like, rotational torque or breakaway torque, it really doesn't play a factor into it. Your vehicle will really not have an issue overcoming the difference in friction from one technology to the other, provided that there's nothing wrong with the joint, right? Of course, we spoke earlier about the creak snapping polymer joints that even are out there, and that's just because the joint has been contaminated and it's worn through. Again, when it comes to the vehicle acting upon the joint, it really doesn't. There's no difference. It wouldn't know absolutely any difference between the two.
The next point, I think, is really the high point, and maybe it needed to be number one, but self-lubricating. We call it that. It is a porous bearing, and it absorbs, or the grease permeates into it over time. But the real beauty of that sintered metal bearing is when you pair it with or you compare it to a standard metal-on-metal design. I always like to say that the Achilles heel of a metal-on-metal design is the grease zerk. You neglect to grease it, now you got two pieces of metal working against one another in a short time period. The beauty of the sintered metal bearing is, let's say you greased it the first year, the second and the third year you neglect it. As the lower bearing wears a little bit, you've got a little bit of lubricant embedded in that or permeated in that, and it comes out as the lower bearing wears and just increases the wear life of that joint, whatever it may be, in a ball joint, a tie rod end, a control arm, tremendously. So that part of it is such a game changer if you happen to neglect it. I'm not going to say do that, but when that happens, and how many grease zerks are on vehicles now, and our younger technicians are not being trained to look for them, even though we know it lasts so much longer if you put a little bit of shot of grease in it, here and there. So I think the self-lubricating portion of it is such a game changer, because if we happen to neglect it, one or two services, it's still going to have that good wear life.
Yeah. We do have a question that came through that I think falls right into what we're talking about now in terms of, and it's a question we get through the tech line a lot. I'm sure, Mac, you've gotten how much grease do you put into these things? Now, I know a lot of people will think like you pump them full of grease, you want to see that boot swell out. Unfortunately, a lot of people have the misconception that a ball joint boot or the boot itself is a reservoir for grease. Yeah. Unfortunately, usually the way these ball joints are positioned, gravity will never allow that to happen. It's just a waste of grease. You really want to just add grease slowly until you see the boot swell slightly. Once you see a little bit of swelling happen in that boot, you know that the grease has made its way around the bearing surfaces, around the sphere, and it's where it needs to be. That's where it does its job, is between the bearing surfaces and the sphere. It does really nothing when it's sitting up in the boot. And in fact, it's actually kind of detrimental to the boot, because what will happen a lot is it'll swell and balloon the boot out. And now that boot gets rubbed by the knuckle or rubbed by the tie rod end, and it can actually tear through, and then you actually compromise the part. So if it ever happens that you actually do over-grease a part accidentally, or let's say you're trying to flush it, majority of serviceable parts will have grease reliefs into them, We technically put them on the side of our boot. It's a little block that comes out. And it's just a matter of kind of squeezing at the boot a little bit and expelling some of that grease so that the boot is in its relaxed position. You don't want it to be ballooned out. So again, just grease it up until it moves slightly. And again, a small stabilizer link might take a half a pump of grease. Yes. A larger ball joint may take up 4 or 5. So it's really playing it by ear and looking at for that boot movement.
Yeah, application specific. Now that's a really good point because it can be detrimental to overfill it.
Yeah, and one other thing while we're on this topic is stay away from electric or pneumatic grease guns. Those things are built for backhoes and excavators where you literally got to pump almost a Coke can's worth of grease into a joint, and you don't want to sit there going like this. A ball joint, again, it's 10 mils of grease. It's literally what you put on your toothbrush. You don't need an electric toothpaste dispenser at home. We don't need a pneumatic or electric version in the shop. The amount of grease is just too small. And actually, the volume and the rate at which some of these pneumatic or power grease guns can put out, you can actually maybe damage it. You can fill it up too quickly, hydrolock parts sometimes if the grease can't get out quick enough. I showed the grease channels. They're very, very thin. There's only a certain amount of grease you'll be able to push through a grease channel. So stay away from those. The hand pump is the best way to go because we're only using a small amount of grease. And the last point is what type of grease, Mac?
Yeah. I get asked this often in the field, along with how much should I grease it? Any of your GL or GCLB grease is compatible. It's fine. You don't have to put a synthetic or a high-end grease in it. I would say the most important thing is that you're greasing it often.
Yeah. And GCLB is just the new term for number 2. It's what everyone used to call number 2 grease, right? So now to the cons. There are some. They do require more space than plastic. Of course, they're bigger, they're bulkier. It is a piece of pressed metal or powders into metal, so you can't make them razor thin. They will shatter or break at that point. So there's a minimum amount of material that you need to use. But it's always, it does take up a little more space. So there are compromises sometimes that need to be made.
Right. And the next point, of course, it is a little more challenging to manufacture this design. Even though we know it's going to last longer, it's going to hold up, it's better all the way around. It is a little more challenging to manufacture it. The manufacturing process is not as simple.
And it is more costly to manufacture. A couple of grains of plastic beading to make polymer. The recipe to make a sintered bearing, it depends on the amount of zinc you put in, how much iron you put in, how much copper you put in. You get different results every time. And, sometimes to put up with the larger, heavier vehicles that need a little more wear resistance, a little more impact resistance, it does drive the cost up. And just, again, all around, it's not a one stop and go. You got to mix the powders, press the powders, sinter the bearing, and then it gets checked for imperfections and surface cracks and whatnot. So it's a much more lengthier process. But again, it's the effort we're willing to put in to provide something that's going to be much more beneficial in the end, right? And the next, go ahead.
This is also, if you figure these are being put on older vehicles with more miles on them and more other components are more worn out, that ball joint's not going to see the same sort of life cycle and load stresses as it may have on a new vehicle.
Yes, definitely. That's exactly.
Brian, what you just said, I wished I could have packaged that for the years I have my shop and hit a little recording, a little response, because it's so hard to communicate. And Victor and I say it all the time, that vehicle that you have in your repair shop is not the same vehicle that rolled off the assembly line. 7, 8 years, 9 years down the road. And most of the time, we're replacing the part that's broken or failed. The other components that wear with it, you just described it beautifully. Maybe they're 85% done. Maybe they're 60% done, but they're further along, and it changes things drastically.
Yeah,
definitely. So here's a little bit of side by side to kind of go through. Just the three main competitors right now, what you're going to find out there, right? Again, metal to metal, we've been through it. It was a good technology for its time. It was something that was a step up over the steel plate and spring design. It is cost effective, but there is a huge amount of reliance on that lubrication lining that needs to exist. It's pretty much like your crankshaft or your camshaft. As long as the oil's flowing, everything will be good. You cut that oil off, and man, it doesn't last very long until you throw a rod or you burn something out. And that's pretty much its major downfall. It's outdated, unfortunately, and that's what true metal on metal is actually considered. When it comes to the polymer bearing, again, great friction properties. It lasts the length of the warranty period for the manufacturer, and it is easy to manufacture. I did want to bring up a point. In our list of pros and cons, if you saw the pros and cons in the plastic, you'll notice that all the pros benefited the vehicle manufacturer. The cons kind of went against the vehicle owner. When you look at our pros and cons list between sintered bearings, you'll notice that the pros are for the vehicle owner. The cons go against the manufacturer. It's really just kind of goes to show that the product is really being developed and used for a positive outcome on the service end of things. And that's why they are, again, we use them for reasons like them being impervious to heat. They're durable, the good impact loading. They got the same good low friction properties and that serviceable feature. Again, somebody chimed in and said, best practice, clean off the Zerk fitting before connecting the grease connector. And, thumbs up for that. That is definitely, I don't understand why somebody would just go and plug in and push all the sand and dirt right on the end of the Zerk fitting, right into the joint and just compromise it. That's why actually our TTX grease Zerks come with little caps to try and keep them clean. To prevent that from happening. But a great point there. I just wanted to bring up while we were on it. Now this is actually some testing data. So we'll look at the yellow line first. That's your metal to metal. And after roughly about 50,000 cycles, we had 1 millimeter of deflection. Not the greatest kind of track record to have. Our cycle testing is pretty much grabs the ball joint, it does all 4 motions and a twist, and then rocks it. So that's 1 cycle. So it got through that 50,000 times before it hit 1 millimeter. The next one was polymer. It kind of made it to about 150,000 cycles before it got to that 1 mil. The sintered metal that we use in our Supreme bearings made it well past down the line before it got to 1 millimeter. And then the recipe that we use for our TTX or terrain tough ball joints, which is really, really formulated for service life and dedicated to that, really went off the charts well past 1 million cycles, and it kept going. So again, just to kind of put some testing data to everything we've been speaking about, it's not just kind of hearsay, that there is some actual work being done to prove the testing grounds here.
And here we are creeping up on our 60-minute mark. In just a few moments, we're going to start our Q&A portion of this webinar. But before we do that, I'd like to ask everybody to just take a moment and fill out the survey. The survey should be popping up on your screen at any moment now. If it doesn't launch, you can click the survey icon in the toolbar at the bottom.
All right, well, finishing up here, you know, why centered bearings are superior. I think we're kind of not beating a dead horse, but we really pointed out the advantages. And, you know, of course, it's going to be about 3 times longer than your plastic or polymer, and 10 times longer than that metal on metal that's milled out of the housing. So just a superior design and great from a wear life standpoint.
Yeah, they're capable of handling high loading and impact. So again, for your working vehicle, for the vehicles, as Brian, you so eloquently put earlier, that are just older, the stuff's working against itself. It's definitely not the same thing as it came off the assembly line being. It's definitely, they're much more prepared for that.
And again, the part that is just really a plus that sometimes I think needs to be number one is Victor pointed out and showed it wasn't shiny when the bearing was cut open or when it was sectioned. So the spaces within what we would call the grain structure of the centered metal provides continuous lubrication, or an area where as you grease it, it kind of permeates into it over time. And I think that was a really good description of, you could just keep wiping it and you're never really going to wipe it clean. So the beauty of that self-lubricating bearing is if you happen to neglect greasing it, again, it just increases the wear life tremendously.
Yeah. And another good important thing to know is that when you're using sintered bearings, any GCLB grease can be used to service the part, and you don't have to worry about damaging the bearings. You can really use any type of grease, whether it's synthetic, lithium, whatever it may be. You don't really need to be concerned. Any grease that conforms to GCLB standard or number 2 will work properly and really rejuvenate the part, help keep it going in service.
And of course, last but not least, can operate in a high heat environment without deforming or without degrading. The heat's not going to be a challenge or an issue with that. I'd say if you have a centered metal bearing or a control arm or a ball joint in an area where heat is around there, maybe you do yourself a favor and you shoot a little high temp synthetic in there. But the design of the centered metal bearing, it being self-lubricating, is just going to far outperform anything else that's out there in the market or field.
Yeah. All right. And so I guess we can kind of chime into some of the questions that have come through that we haven't been able to get at.
Yep. If anybody has any obligations, of course, this a recording of this webinar will be available on the Shop Owner brand websites within the next few days. Feel free to log in and view it later if you do need to step away from your computer, or encourage your colleagues to view it. Also look for a follow-up email directing you to that on-demand version of the webinar. Now, we've got a couple of questions that we're going to try and get to here in the next few moments. I want to start with Cam here and Dennis, but I'm going to combine these 2 questions together. Is additional grease required during initial installation? And then once you put the initial grease in, does it ever leave?
So to get to the first part of it, they do come pre-greased, and usually there's adequate grease to get it going into its service life. And if you forget to grease it or if you don't grease it, it's not a big deal. It'll hold off until you get to your next service cycle or anything like that. However, as a technician, I always found it best practice. You know, it polishes off the job. You go in there, you add a pump of grease. You know you've done your due diligence and everything's great on that end. So you don't need to, but it can't hurt at the same time.
Yep. I know that everything at my shop, same thing. I'm always putting a couple of squirts in it just because that was my name rolling out.
Yeah. Now, to say that the grease never leaves, that's true. It does stay inside. There is usually a release valve in it so that any added grease that kind of gets in, you can expel to the point where, you know, if you're in and out of muddy situations, you get a little too deep putting the boat into the water and you soak your ball joints, You can pump grease until, like I mentioned earlier, the balloon will swell out, push down on it, expel the grease out, and kind of cycle grease through it. So it can go in. It has to have a way to come out. But as long as it's not anything's not torn or wrong, the grease should stay inside.
Very, very good. And a question / comment here from Peter. He talks about the fact that weight differences. We're talking about lightweight and cost savings. All of these benefits, or all of these pros that benefited the OEMs, and they go hand in hand. I can speak to that. I know the wisest words ever spoken to me, spoken by my first mentor when I started wrenching years ago. He says, vehicles, motorsports, any machine, they are engineered and designed to be assembled, not worked on. And the OEMs, they've got much different design criteria than companies can in the aftermarket. They're looking at that warranty period versus the cost versus the weight, where an aftermarket company can focus on that user experience, that vehicle owner experience.
Right.
Definitely.
You know, I'm glad that question was asked, because sometimes in the field, I'll have technicians respond and say, well, they're designing it on purpose to fail. And there's kind of a little bit of truth to that, but the restraints or the goals that they have are driven by cost restraints, and it just has to last this long. Sometimes it lasts longer, but you're right. They have a different criteria, and what they're looking for is, can we make this cost effective? Can we make it last at least 336 or 550, whatever it may be? And sometimes it gets out of that and does well, but a lot of times it's the OE criteria drives a different agenda.
Absolutely. Right. And that is about all the time that we have. For any of the questions that we didn't have a chance to answer live, you can look for a direct answer for that at a later time. This concludes our webinar. I want to thank everybody for all of your time. Thank you, Victor and Mac, for joining us. And everybody, have a great day.
Thank you for having us. Take care.
Yeah, thanks, everybody.